Hello everyone, welcome to topic 9.7, Galvanic, Voltaic, and Electrolytic cells. By the end of this, you should be able to explain the relationship between the physical components of an electrochemical cell and the overall operational principles of a cell. So this is an introductory section for electrochemistry. So electrical energy can be generated from chemical reactions. In an oxidation-reduction reaction, electrons are transferred from one species to another. We saw that in Unit 4, maybe 2. We saw that earlier this school year. One way to harness this electrical energy is to create an electrochemical cell, as shown below. A chemical cell is a simple cell is set up as shown in the image below. In each beaker, there is a metal or a gas system and its corresponding ions in solution. In a standard cell, the concentration is 1 molar at 298 Kelvin and 1 atmosphere. Please note that that temperature is different than STP temperature, which is 273 Kelvin. Right, this one is STP. This is standard conditions, a little different than the STP. This is referred to as a half cell, where we have the metal or gas system and the corresponding ions. So this is a half cell. This is a half cell. Put them together and you have an entire electrochemical cell. These will not react unless the two are connected to complete the circuit. And so this salt bridge that we see in the middle connects them along with the electrons here. So we see that they flow and charges are allowed to continue to flow here, which completes the full circuit. Solids or gas systems that are placed into each of the solutions are called electrodes. So this is an electrode and this is an electrode. The electrode where oxidation occurs is the anode because it attracts anions from the salt bridge and the solution. The electrode where the reduction occurs is called the cathode because it attracts cations from the salt bridge and in the solution. The mnemonic that can help you to remember this is red cat and ox. Reduction occurs at the cathode. The anode has oxidation. Electrons flow through the wire from the anode to the cathode, so there's another mnemonic, fat cat, from anode to cathode. So from anode to cathode, okay, to indicate the direction of electron flow. The salt bridge or porous disc that is sometimes used to separate solutions. So sometimes there's like a little cup disc that sits between two things that'll separate them, but we'll usually work with the salt bridge because it's cheaper. The ions in the salt bridge will travel through the solution, agar, or glass wool and serve to maintain the neutral charge as the electrons flow from one side to another through the wire. Without these ions in the salt bridge, the reaction does not occur because it helps maintain electrical balance. If there is an electrical balance, the electrons can't move from one side to another. A porous disc between two beakers works similarly without the need for another solution. The ions are able to travel between the two sides. To predict which of the potential reactions is thermodynamically favorable, right, we've been talking about, gives free energy, and now we're going to apply that to electrochemical systems. We need to look at a table of standard reduction potentials. On the AP exam, the values are provided in the problem. You could also find the table in the link here. I will print that for you in class. The table of standard reduction potentials is basically a ranking system of different substances. The ones that are best at reduction, or most likely to be reduced or gain electrons, are at the top of this chart, while the others that are not as good at reduction, or the worst, so are least likely to be reduced or gain electrons, are at the bottom. The substances at the bottom, since they suck at being reduced, they rock at oxidation, so they are the best at oxidation at the bottom. The electromotive force or reduction potential So the difference between the two half cells, that's the reduction potential, gives the voltage that is generated from the half reactions. Let's compare two substances, silver and gold. So this is how they note the half cells, what they contain. And this is the electrode and the ion in solution. So electrode, the solid part, and the ion in solution. They should usually match, but we also have to indicate which ion it is because the number of electrons that are moving will also impact the reduction potential for the electrochemical cell. So if we write their reduction potential equations, so the reduction reactions, we can look up their standard reduction potentials on a table, and we can compare them. So we see that this one is greater than this one. So if you turn your paper on the side, it's like this one's going to eat this. I don't know if we remember that from grade school, that the crocodile will eat the bigger one. There's my crocodile, guys. Maybe more like a dinosaur dragon. Since it is bigger, it is better at reduction, and so it stays the way it's written. The other one, our loser, is better at oxidation, so we're going to flip it around and rewrite it as Ag, as an oxidation reaction for this. When we do that, we will see that this will change to a negative sign, and we'll come back to what that means in a minute. The reduction reaction for the gold ions has a higher reduction potential than the silver, which means that gold ions are better at being reduced than the silver ones. We can use this to predict the thermodynamically favorable reaction that will take place, right? So since we flip the silver reaction, we end up getting this one when we add them all together, but we also notice that there is a coefficient change, and we'll get back to that. Since this one puts them both at what they're better at, well, not necessarily better at, but we'll see produces a positive reduction potential. This is the thermodynamically favored reaction at top. But if we flipped the other one, so if we flip the gold reaction, we end up seeing that it is not thermodynamically favorable, so it's unfavorable and does not react. Because we know the reduction potentials, we can also predict the voltage that will be generated when the reaction occurs. When we flip a reaction, as I showed for silver, to switch the position of the reactants on the products, we flip the sign for the voltage. However, when the reaction is multiplied by a factor, as we would have done here, so we multiply by 3, so that way we have the same number of electrons being produced or being consumed and produced. So when we add the reactions together, they cancel out. We do not change. Notice I only changed the sign. My apologies. We only changed the sign here. We do not multiply by 3. Okay, so if you flip the reaction, you only change the sign. We do not multiply by a factor. So then for the thermodynamically favorable reaction, gold ion plus silver solid yields gold solid plus silver ion. It generates a positive 70 volts, okay, because we add these together. And we get 0.70 volts. Because this is positive and our cell potential is positive, this is thermodynamically favorable, and these are known as galvanic or voltaic cells. They're both used interchangeably. Whereas the unfavorable reaction, if we took this one and we flipped it around to go the other way, right? This requires, so our E cell for this one, so this is the volts for the cell, it flips its sign because we flipped the reaction. We see that it's going to require 0.7 volts. My apologies. I'm having a hard time talking. Cells that are unfavorable, so this is unfavorable, have negative voltages and thus require external power supplies and are known as electrolytic cells. Okay, so we're going to apply that to these practice problems. So looking at this for our ID, we are given the half reactions for magnesium and sodium. We are first going to write the thermodynamically favored balanced overall reaction. So when we compare these two, the one that is more negative or smaller is going to be the one that is least favorable. So if we look at this, we see that this one is more negative, so it is our loser. So we're going to flip this around, which means that the sign is going to become a positive sign. We also see that we have 2 electrons here, but not the same number here. Part of this, we have to make sure our electrons, when we add them together, cancel out. Electrons are produced and consumed in the same reaction, so we shouldn't have a net gain in electrons. So we should then multiply this by 2, so that way our electrons cancel out, right? So we cancel these out, okay? But we're also flipping the bottom. So if I write the top first, so I have magnesium 2+, because I'm not flipping it, so I'm going to write it first. And that's going to make the magnesium solid, right? And then I'm going to write my second equation, but I'm going to add all of this together. And I could do this and like show all the process, but we're trying to save some room because it's tiny space. Since I'm flipping the bottom one, that means my products are now my reactants. And then this one is a reactant that is now my product. And a way to check that you did this correctly is not only are your elements balanced, each of your atoms balanced, but the total charge on both sides is balanced as well. So I have +2 plus 0 is +2 on this side, and then 0 plus 2 positives is +2 on this side. So because they both are +2, I know that I have the same number of each atom on both sides. I did this correct. So now we're going to calculate the voltage. So the E cell for this is the sum of these two. So the negative 2.37 volts plus, and it's positive 2.71 volts. Because I flipped the equation, I've changed the sign on this. It was negative, now it's positive. And you should end up with a positive 0.37 volts. Now, normally we wouldn't write a positive because by not having a negative sign there, we know that this is a positive value. But because the thermodynamic favorability is really based off of this sign, it is a good idea to add it there so you're emphasizing the fact that you know that that is positive. It is not something that is required, but it's something that is good practice. Okay, so write the half reaction that takes place at the anode. Let's remember that the anode is where oxidation occurs. So we're going to look at these two and see which one is the oxidizer, or not oxidizer, the one that is being oxidized. Remember that the one that's being oxidized is the one that loses the reduction battle, and that means that we flipped it. So in this case, it is our sodium, and so we write it 2Na yields 2 sodium ions plus 2 electrons. Remember, we flipped this so that way we can have our half cell. So this is the reaction that takes place in the anode half cell. And it should be oxidation, which means it produces or loses electrons, right? So since it's making electrons, electrons are produced because they're on the product side, it is losing those electrons. Now, if we write the reaction that takes place at the anode, that is the reduction half reaction. And so we look at the top, and it should be my other half reaction. So I'm going to write my other half reaction, because these are a list of reduction potentials. And we end up with this equation, the reduction of magnesium. And we know it's reduction because it uses or gains electrons. So after the reaction has been allowed to take place, what happens to the anode? Well, I look at my anode, and I go from solid to aqueous. So my anode electrode should lose mass. okay, because it's going from solid to aqueous, which means it's moving into the solution. So if we look back at the drawing on 2 pages ago, it's not wanting to scroll for me, but we had our cell beaker and it had an electrode in solution of the ions. So this would be like sodium and the sodium solid, right? And because it's eating away and making more aqueous, it should lose mass. After the reaction has been allowed to take place, what happens to the cathode? Well, the cathode's going to do the opposite, right? If we look at the cathode reaction, we take parts of our solution, like the ions in solution, and we make solid. So the cathode electrode gains mass because I'm making solid, and it plates right on the electrode because that's where the electrons are going to come into contact with the solution. And we'll dive into this deeper as we move into the unit and do some additional labs. But it gains mass and becomes bigger. Okay, so using these concepts, we're going to complete the you-do one step at a time. So I want you right now to pause the video and complete part A for me, and then resume when you're ready to check your work. Okay, and so you should have seen that this being the worst at reduction will be the equation that we flip, right? So the more negative or smaller E or reduction potential is the one we flip because that'll be better than the other at oxidation. And so we see that we have electrons on both sides of the equation and they are the same, so we'll cancel them out and write what's left on both sides of the reaction arrow, adding these half reactions. And so you should get the 2 hydronium ions plus iron solid yields the iron ion plus hydrogen gas and water. So now using this, please calculate the voltage for the cell as well as write the 2 half reactions that take place, one at the anode and the other at the cathode. Pause the video and complete this now. Okay, so you should have gotten that the voltage for the cell is 0.45 volts and that is positive because we picked the favorable reactions out of the 2 pairs. Then when we write the half reaction for the anode, it is the iron half cell. When we write the half reaction in the cathode, it is the hydronium forming water half cell. We include the electrons in these because the half reactions produce or consume the electrons and we have to write them to fully account for what is changing. So now for E, after the reaction has been allowed to take place, what will happen to the anode? The anode's electrode will lose mass, and this is always going to be the same no matter what the anode is. The process is always going to produce something that goes into solution and leaves a solid, so it'll lose mass, right? So then after the reaction has been allowed to take place, what happens to the cathode? Traditionally, we would say gain mass, but if we look at what's actually happening here, we should see lots of bubbles too. So we may actually, if we had a closed system, to pay attention to the amount of gas, we're going to make more gas, but we also should see a mass increase in the gas area for the cathode. That one's a tricky one. Okay, so now paying attention to this and referring back, you are going to complete the you-dos using the notes and examples we've gone over. Check your work, and thank you for tuning in.